Hey there, hello and welcome to another episode of Short Takes 331. Today we're going to talk about matrix vector and matrix multiplication. And most of what I want to talk about today is the operational aspect of it. So how do you do it? So by matrix we mean an array of numbers that looks like this. It's basically a square rectangular array of numbers, and here we have n columns and m rows. And so we have m rows and n columns, and this is what we say is a matrix that belongs to a set of, I don't know, real numbers, complex numbers, what have you, to the power m times n. So this is what we mean. For example, here, if m is made out of real numbers, we say that m belongs to r to the m times n. And so you would have here numbers like 3, 4.7, pi, and so on and so forth. And that's what we mean by a matrix. It's simply an array of numbers. Now, given a vector of size n, so n rows, here we define the product of a matrix like this one by this vector in this way. So we set them next to each other as you do with the product, but then the result is calculated in the following way. We take each of the elements in a row and we multiply them one by the column of the vector, that is the vector, and we sum them all up in this way. So you see here m11 with x1, so this is this guy here with this guy, plus m12 with x2, so m12 with x2, and so on and so forth, all the way to the last one times the last one. So you go by row and by column like this, you multiply them one by one, one against the corresponding one, and 1 with 1, 1 2 with 2, 1 3 with 3, and so on, 1 n with n, and then you add them all up. What do you do next? You go to the next row and you do the same thing, and then at the bottom you go to the bottom row and you do the same thing, and then you get the final row. And so you see the result of having n elements multiplied by a elements and add it all up goes at the top, and then you go on down the rows, and in the end, because you have m rows in this matrix, then you end up with m elements here. So this is important to know. A matrix of size m by n can be multiplied by an n component vector, and the result is a matrix, or rather vector, of size m, so m rows. So for this to work, the number of rows, the number of columns of m must equal the number of rows of the vector. The number of columns of m in this case must be the same as the number of rows of x. So you see we have n rows here and we have n columns here. So that works out. In this case, if you don't have that, if the number of columns of your matrix does not equal the number of rows of your vector, you cannot multiply one by the other. It's just not defined. It doesn't make sense. Okay, the result then has m as the number of rows in the resulting vector. So let's see an example of this in a case that is very simple, where you have m rows and n columns where m and n are both equal to 2. It's a very simple example. It's what we call a 2 by 2 example. And so here I have a matrix which is 1 2 3 4 multiplied by x1 x2, and so I'm going to take 1 by x1, 2 by x2, and I'm going to add them up and get the result there at the top. And then the next row will give me the result in the following row. So 3 by x1, 4 by x2, and I get 3x1 by plus 4x2. And that's it. That's really all there is. It's very simple. It may look tedious the way it's written up here. And indeed, if you have it to multiply a matrix of size 5 by 5 or 5 by 6 or something by a long vector of the right number of rows, of course, you would have a lot of multiplications and a lot of additions, and that's where you really want to use a computer. But up to 2 by 2 or maybe even 3 by 3, it's okay to do by hand. It doesn't take a very long time, but it could be annoying, especially if the numbers in the matrix are not nice and integer numbers as I have here. But if you have some weird numbers with some decimals and so on you have to keep track of, then you really want to use a computer for that to avoid making mistakes. Now, the main point of introducing matrices and the main point of linear algebra really is not so much the arithmetic calculations, but really that these matrices and these vectors are useful to represent linear equations. So to give you an example, this is a set of two linear equations with two unknowns. The unknowns are x1 and x2. They satisfy these two equations. We want to solve these equations. In a 2 by 2 case, of course, you would solve for x1 and then take that result and put it in the next equation and solve for x2 and that way, and then solve for x1 at the end, and so on and so forth. It's very simple to do. It's a 2 by 2 system. If the systems get large, that is a very tedious thing to do, and so we have to resort to more advanced methods. And this is, again, the point of linear algebra. Now, how matrix vector multiplication helps, it helps because we can represent these two systems of equations in a very compact way, as you see here. So here I took the same matrix that we had in the previous example, and I showed that if you have 1, 2, 3, 4, which was the result here, as the coefficients, then suppose that you have this type of system of equations, then you can represent it by saying that this matrix by this vector has to equal the right hand side, which is 7 minus 2. Because by doing this operation, 1, 2 by x1, x2, and 3, 4 by x1, x2, you obtain this result up here. And this equal to 7 is the first equation, and the bottom equal to minus 2 is the next equation. So you see that this is a very compact way to represent a linear equation. And something that I didn't write here, but symbolically you can understand, is that solving for x1 and x2 amounts to doing something to the right hand side so that you can put this on the other side of the equation. Or another way of saying that is that we want to put this whole object on the other side of the equation, because that would amount to solving for x1 and x2. If somehow I manage to get this on the other side of the equation here and act on this vector with what would be the inverse matrix, then I would have solved at that point for x1 and x2, and I would have the answer. So this is something that we're going to learn to do in upcoming videos. For now, I'd say if you enjoy these videos, please consider liking and subscribing. This is a series of videos meant for my students at UNC Chapel Hill. But if you're not a UNC student and you need help with physics or math in English or in Spanish, you can send me a message at shorttakes331@gmail.com, or you can leave a message in the comments section below. Now, I want you to notice when you do matrix multiplication that what we just described is not the only way to do it. You may also write matrix multiplication by thinking of the matrix as a set of columns. So imagine our matrix M now as a set of columns that I'm going to call M1 vector, M2 vector, M3 vector, and so on. So imagine that these are column vectors, and I use arrows here to represent that there's numbers coming down here which are contained in this vector, and so on and so forth. And so you can convince yourself that actually taking the product of a matrix by a vector and thinking of the matrix in this way amounts to doing this calculation. Taking x1 and multiplying by the first vector, and taking x2 and multiplying by the second vector, and then adding it all together. And you can see that, for example, in the previous example that we saw in here. So you see 1 and 3 are both multiplied by x1, and 2 and 4 are both multiplied by x2. You see here. And so that is the principle that's behind this more general statement, that is, it's always possible to do that. Okay, it's always possible to do that as long as you have n columns and n constants here in your vector, so the sizes are consistent with the definition of matrix vector multiplication, then this is always true. And this is super useful. It shows that the resulting vector, so this whole thing added together is one vector when you put it all together. This resulting vector is just a linear combination of the columns of M. That's all there is. When you multiply a matrix like this by a vector, all you get is some linear combination of the columns, linear combination with coefficients given by your vector. This is very useful to know because we'll be interested in cases where this linear combination, or rather these column vectors, are linearly independent. We'll be interested to find out if they're not linearly independent. Then then we can answer the question, can I represent any vector as a linear combination of these guys or not? You see, this would have repercussions on the answer as to whether m times x could be equal to some right-hand side that we are given. If it's possible to solve for a right-hand side, it means that we can represent that right-hand side as a linear combination suitably chosen. This x is what we're trying to find out, right? This is what we mean by suitably chosen. Suitably choosing these x's is possible to find a linear combination that would give us that right-hand side of the linear equation. Whether that's possible or not, it depends on the matrix and it depends on the right-hand side. And we will see more about that when we talk about solving linear systems of equations, which is the whole point of, or a majority of the point of linear algebra. Now here, as I said at the beginning, we're focusing on the mechanics of matrix vector multiplication, and we'll talk about matrix multiplication as well. And so let's see another example, a more numerical example, and in particular applying this type of technique that I mentioned just now, the linear combination of the columns. So let's see how this works out in this example with 2 by 2 matrices. So suppose you have this matrix 7, 1, 10, minus 1, and you want to multiply it by the vector 2, 3. If we do it the conventional way, then we get 7 times 2 plus 1 times 3, that goes on the top. And then 7 and then 10 plus times 2 plus minus 1 times 3, that goes on the bottom. 10 times 2 plus minus 1 times 3. And you do the calculation, and oh, what do you know? You get 17 on the top and 17 on the bottom. If I did everything correctly, that's 14 plus 3, that's 17, and that's 20 minus 3, and that's 17 as well. Actually, when I came up with this example, that was completely accidental. It just so happened. So maybe 17 is some kind of lucky number. Now, on the other hand, we could say, let's take this column vector multiplied by 2, plus this other column vector multiplied by 3, and then add it all together. Well, this first one is 14 and 20. That's pretty easy to figure out. And this other one is 3 and minus 3. And then we add it component by component, and we get 17 and 17. Correctly, it's the same result, of course. It's the same type of operation, but we did it in 2 different ways. And sometimes it will be useful for you to know more than one way of doing things. Of course, it's more than one way of understanding things. It always will make you, you and your math more powerful. And so it's good to know that you can do things by row and column, or by columns and multiplying by the rows one by one of the vector. So that's it for the example. I hope that makes sense, but you should come up with your own examples and think about how things work where maybe you have some zeros, or maybe it's a 3 by 3 case. And what if the matrix is not square? Okay, think about examples where we vary a little bit what we're doing here. That will always be useful for you to better understand what we're doing. So here's another example. Consider the unit matrix, what we call the 1 or I. Sometimes I will write it as a 1, sometimes I will write it as an I. And it's a matrix such that its elements are given by the Kronecker delta ij, which means that it's equal to 1 if I is equal to j, or 0 otherwise. And so if I is equal to j, that means that the row is equal to the column number. We're talking about the diagonal in that case, and that diagonal is given by 1s, and everywhere else there's zeros. So that's what we call the unit matrix. And the main property of the unit matrix is that if you multiply that matrix by any vector, you get, you might have guessed it already, you get the same vector. That's what's called the unit matrix. It doesn't do anything. It's like a 1. It really acts like a 1, and it commutes with every other matrix and so on and so forth. And we'll come back to commutation of matrices in just a bit. I'm getting a bit ahead of myself. So the unit matrix then is given by, this is a special matrix if you want, and we'll use it quite a bit. So let's talk about matrix multiplication, which is what I was just mentioning slightly by getting a bit ahead of myself. So here, let's say that we have matrix A that is made out of real numbers and it's of size m by n, and B is similarly real and of size n by p. We define the product of two matrices A, B. Notice the consistency in the sizes, n over here and the number of columns, and here n in the number of rows. We define this vector, this product AB, by saying that the elements of such a product are given by this result. Again, the elements of this product matrix, element ij, is given by the sum over k from 1 to n, a, ik, b, kj. And here I goes from 1 to m, and j goes from 1 to p. And so the resulting matrix will be of size m by p. Okay, AB is a matrix of size m by p. And what happened with the n? The n got absorbed into this operation of summing over all the columns of A and all the rows of B when you do this calculation. And so in full-fledged form, which we will use sometimes, but you will not necessarily need to write out a lot of the time. If you can avoid it, then better. So here, better in the sense that it's more compact, whatever you're doing. But here, what we have then is that you take the column and you multiply, the row, and you multiply by the column. And you take the next row and you multiply by the next column, and so on and so forth. And the results then get accumulated on the first row of the resulting matrix. And at the very end, you take the last row and the last column and you multiply them together, and then that would go down here on the bottom. So it's basically what you have here is a collection of matrix vector multiplications, where you take this big matrix and multiply it by this vector, and that goes in the first column. And you take the big matrix and multiply it by the next column vector, and that goes in the next column, and so on and so forth. So you do that p times, and then you get a matrix, resulting matrix of size m by p. It can be a little bit tedious, so let's look at an example. Again, the 2 by 2 example, when we have one of our old matrices, 7, 1, 10, minus 1, that we saw in a previous example, multiplied by 2, 1, 3, 5. So what does that look like? Well, we have 7 by 2 and 1 by 3, and we put it over here. And then the next one over here is 7 by 1 plus 1 by 5, 7 times 1 plus 1 by 5, we put it up here. And 10 by 2 plus minus 1 by 3, that goes here. And then 10 by 1 plus minus 1 by 5, and that goes down here. And then we do these calculations explicitly, you get 17, 17, 12, 5, and that's the result. Now I want you to try to do what's called the commutative product. So you take the matrix here and you put it on the other side instead. So this 7, 10, 1 minus 1 appears here, and 2, 3, 1, 5 appears on the left now. So this matrix appears on the left, this one on the right. Try to do this calculation. And this is supposed to show you that matrices generally don't commute. So the product of two matrices will generally not commute. When you do this calculation, you will find that you don't get the same result as if you take this product with 7, 10, 1 minus 1 on the left and the other one on the right. So if you flip the order of the product, you will get a different answer with matrices. The product of matrices is not generally commutative. Now, if you're dealing with a unit matrix, the unit matrix commutes with everything. And we'll talk more about special matrices and what they do and what they don't do in a future video, but you should try to do that calculation and see what you get. You will not get the same answer as here, and it's instructive to figure that out. So here's an example, by the way, of another type of special situation. So here you have a matrix that is 1, 0, 1, 2, and then 1, 0, minus 1 half, 1 half. And if we do this calculation, we get 1 by 1 plus 0 1 by minus 1 half, we get 1. And if we continue in this way, you see that you will get, if you have 1 by 1, 2 by minus 1 half, this cancels out, you get 0. This other result gives you 0 up here, and then 1 by 0 and 2 by minus 1 by 1 half, you get 1 down here. So we multiply two matrices and we get the unit matrix. This is telling you that one of the matrices is the inverse of the other one. This matrix is the inverse of this other matrix, because when you multiply them by one another, you get the unit matrix. And so this one is the inverse of this one and the other way around. And here's another example of a symbolic calculation now with the same matrix multiplied by itself, just twice here, ABCD by ABCD, and what you get is A squared plus BC on the top here, CB by D squared on the bottom, and you get some cross products on the off diagonal. And here you see right away that, for example, if B and C are 0, then you get A and D only to survive, and so you get A squared and D squared, and there's nothing else. And such matrices are said to be diagonal, and those always commute with one another. Diagonal matrices always commute with one another. But like I said, this is getting a little bit ahead of the game. So now that we have some idea of how to multiply a matrix by a vector and what the mechanics of that is, and you should practice it, and the same with matrix multiplication, now that you have some idea of how that works, the mechanics of it, now we're slowly getting ready to talk about special types of matrices like diagonal matrices. We're going to talk more about the unit matrix and inverse matrices and so on. And that has a big impact on the solution of linear system of equations. That's one of the main reasons why one studies linear algebra, but there's also a huge amount of very interesting properties that matrices have that have a lot to do with data analysis and the study of quantum mechanics, and a huge number of applications in physics and beyond. So for now, that's all I have. I hope that you enjoyed this video. If you did, please consider liking and subscribing to the channel. It would really help. And as I always say, if you're not a UNC student, but you need a tutor in physics or math, in English or in Spanish, feel free to contact me. You can find me at shorttakes331@gmail.com, or you can leave a message in the comment section below and I'll get back to you. Until next time.